Welcome in our next period. We see the theorem, division algorithm theorem. Let a and b be integers such that b is greater than 0, b is positive. Then there are unique integers q and r such that a equal to bq plus r. Here r is the remainder which lies between 0 and b. R is 0, r is less than 0 or it is equal to 0. Now here a is divisible by b, we get the quotient q and remainder r. This is the division algorithm theorem. A equal to bq plus r means a is divisible by b, we get the quotient q and remainder r. Corollary of this theorem, let a and b be integers with b is not equal to 0, then there exist integers q and r such that a equal to bq plus r, where mod of r lies between 0 and mod b. Then we see the example. What is say if a and b are integers such that a divides b and b divides a. Suppose a divides b, then by definition of divisibility we have b equal to ma by definition of division. Also b divides a, therefore a equal to nb by definition of divisibility. Now a equal to nb, put the value of b ma, therefore mn into a, where mn is some integer I. Since b equal to ma from this equation, then mn equal to we have 1, but m and n are integers, therefore we get m equal to n equal to plus minus 1. Therefore we write a equal to plus minus b, which is the conclusion of this. Second example, if a, b, c, d are integers with a and c non-zero such that a divides b and c divides d, then we show that ac divides bd. First, we are given that a divides b, then by definition of divisibility we have b equal to k. Also, second, c divides d, therefore d equal to k dash c. Now, we have to show that ac divides bd, therefore consider this bd. Put the value of b and d, therefore we have k into k dash into ac. Suppose k into k dash equal to again integer. Therefore, from this we say that ac divides bd. Since a is not equal to 0, b is not equal to 0. Then we see note. It is so that there are integers a, b, c such that a divides bc, but a does not divide b and a does not divide c. For example, if a equal to 12, b equal to 8, c equal to 3, then we write a divides bc, means 12 divides b into c, that is 24. 24 is divisible by 12, which is true. But a does not divide b, that is 12 does not divide 8. Also, a does not divide c, that is 12 does not divide 3. Second rule, if a, b and c is not equal to 0 are integers, then a divides b if and only if, this is the symbol for if and only if ac divides bc. Then third, if a, b are positive integers and a divides b, then we have a is less than or equal to b. Third, next fourth, any integer is of the form 3k plus 1, 3k plus 2, where k belongs to integer. You take any integer 5, therefore it is of the form 3k plus 1 or 3k plus 2. Now 5 can be written as 3 plus 2. Therefore we write here, or we can write 3 into 1 plus 2. Therefore it is in the form of 3k plus 1. If we take the integer 6, then we have here 3 into 2, 6 plus or only 3 into 6. Therefore it is of the form 3k, like this. The square of any integer is either of the form 3k or 3k plus 1, where k is non-negative integer. The square of any integer is of the form 3k plus 1, where k is any non-negative integer. If we take square of any integer, if we take 4 square 4 square we get it as 16. Therefore 16 can be written as 3 into 4, 12 plus 4, that is 12 plus 4, 16. Therefore 3 into 5, 15 plus 1. Therefore it is of the form 3k plus 1. Here it is written 3k plus 1. Therefore 3 into 5 plus 1, k equal to 5. That is 4 square can be written in the form of 3k plus 1. You can take any integer and write it is in the square of any integer is of the form 3k or it is in the form of 3k plus 1. The cube of any integer has one of the form 9k, 9k plus 1 or 9k plus 8. Like this square you can take the example and confirm the law. The fourth power of any integer is either of the form 5k or 5k plus 1 where k is non-negative integer. 3k square minus 1 is never perfect square for k belongs to integer. The square of any integer cannot be of the form 3k plus 2. The square of any integer is not of the form 3k plus 2. You can take the example 4 square equal to 16. It is written as 3 into k plus 1. We cannot write this as 3 into k plus 2. Therefore, square of any integer cannot be of the form 3k plus